Hi everyone, I just wanted to do, I haven't done a video in a while, so I just wanted to do a video again, essentially because I've moved my code repository and there is some code that might be very interesting for you guys out there as well. So first things first, since I had some problems with my Git repository, mostly due to Dropbox, I know they say don't use Dropbox with GitHub, but anyway I did, so it's moved to peterfelfer/adam-probe code, adam-probe-code. Should be very easy to find it again, and you'll find all the old goodies in there, everything that I've been using. But there's also some new things, and I've already loaded it into my Matlab. And a new thing is mostly that I've written some code that can very easily load data from IVAS in, especially using rrng range files and pos files. Now just show you how to get from your IVAS data straight to something you can use for visualization within 3 to 4 steps, depends on whether you just want to load it in or whether you want to visualize it as well. Very, very simple. And then I'll go a little bit deeper into what you can actually do with the new loader, because I've actually made it very flexible, so it suits a lot of needs of people who do non-standard adam-probe analysis. So let's start with the first things first. So loading in pos variables is as easy as it always was. So you just type pos equals read pos, and you can actually see the command history down at the left bottom. So you can just go and if you're on Mac, you can just drag and drop in your analysis variables. It loads it. So this is a medium-sized data set, about 9 million atoms. And then I will create a range variable by just using the read rrng command. That's new. Okay, so that's new. And unfortunately, Matlab is case sensitive when it comes to file extensions, which is bothering me a lot. But anyway, you just might need to set your rrng reading to lowercase or uppercase, depending on what it is. And what you get if you do that is actually a variable that has all of the ranges in it. And you can see it has the range names, master charge begin, and volume for reconstruction, so volume of the ion in the reconstruction, what atoms are contained in there. So you could, for example, go in the H2O and you'll see there's an H, there's an O, which atomic number and how many of them. But mostly it will actually use the range name thing, and we'll get to that later. And it also contains the coloring information, and that can come in very handy. And then in order to be able to work with the data, all that you need is a decompose by range command, and I'll show you the details a little bit later. First, let's just use a decompose by range command. I've made it very flexible, so it's not as fast as it could be if I made it a little bit more specialized, but in this way it actually helps everyone to understand everything very easily. And we can see here is you've got all your different variables now here. So you've got one pos file for the boron atoms, one for the carbon atoms, and so on and so forth. And you can see I didn't call it atomic decomposition, I call it type decomposition. Why, I'll get into later, but for now that's all you need to know. And if you then want to visualize it, very simply, there is a plot APD data command, and you can use the coloring information. So the plot APD data has 4 inputs. The first one is the atomic positions you want to show. The second one is the fraction of those you want to show, so the sample size. And if it's smaller than 1, it takes a fraction. If it's larger than 1, it takes the count. So if you want to have 10,000 atoms displayed, type 10,000. If you want to have 10% of all the atoms shown, then you can type 0.1 like here. The next thing is the coloring. You can explicitly tell it what color you want by just using the usual, RGB value. So 001 would be blue, right? But we can use the rng variable, and it will search if there's an aluminium color. A color for aluminium, and if there is one, it will use it. And the last bit is just the size of the glyphs. So this is for units, I think it's pixels. Anyway, you want larger dots, larger number. You push that, Then you get an atom probified axis system, so everything is white in the background. Then the z-axis is inverted, and it will straight away plunge you into rotation mode. Okay, very simple. Gets you started in Matlab with your atom probe data very quickly. And the good thing about it is you can use all of the analysis files. This would be a typical analysis folder from IVAS, and do very large batch processing. So I've partially made that so that I can have a piece of code that goes through all of different projects and pulls out things like, is there a correlation between background noise and in the data and pressure of the experiment, stuff like that, batch processing. Okay, so that's about it if you're just fundamentally interested in how to do that. The next thing I'll show you though is what the Decomposed by range does. It does a couple of things, and the first thing is it takes your parent POS file, POS variable at this point, and splits it up by different means. So either just by each individual range or by range name. And why a range name is kind of similar to ions, very similar to ions, and I'll show you why. And the third one is called type, which is very similar to atomic decomposition. So you get, as you can see here, you get one variable per atom type. Okay, and what you additionally get is you get a file with all range. So all range contains all atomic positions out of the POS file that have been ranged. Which is important for concentration calculations because you don't want to include the non-ranged atoms because they're noise. Okay, and you get one variable that says atomic concentration, so it just can easily go in there and see, what the concentration of the individual things are. Okay, so let me just close the GitHub now that you know where to find everything. I don't think we need that anymore, and I'll just close that up as well. And, so if we go in the Decomposed by range, then you will see you have the three different possibilities. So you've got Decomposed type range, which is very straightforward because you get one post variable per range, and it's actually named after that. So let's just do that. So let me clear out the variables and read in the post file again. And read in the range file. Oops, range is read range. And again, lowercase, uppercase. And let's read that in. And if I now go and decompose by range and go range, what it will do is very simply spit out one variable per range, as I've mentioned before. And what it means is very often you get a lot of variables, and the variable will not just have the range associated with it, but it will also have the rounded starting mass to charge, so that you can tell, okay, this is aluminium around 13, this is aluminium around 27, aluminium around 9, right? So they don't have to go and guess, okay, which one's the 1+, 2+, 3+, and so on and so forth. Okay, so if you work on a per range base, that's something you can very easily do. Then the next thing is, of course, decompose, and for now I'll just leave the variables in. I hope you don't get confused too much about it. So the next decomposed type is, how did I spell it, range name. And what that means is actually that it splits it up by, as the name suggests, range name. So how's the different by then splitting up by ion? And the difference is you can actually do things. Okay, so for example, we've got boron pos now. We've got, now that we've split it up by range name, we've got also an H2O pos. Okay, that we didn't only had the H2O 18 pos before. Now we've got the H2O pos. And the same thing, like all of those different ones that are essentially the same ion type, they're all now one variable. So all of the molybdenum ones are now one molybdenum variable. The reason why it's range name is because you can go into the range variable and you can rename ranges to whatever you like. So you might have ranges that are not necessarily representing atoms. So you might have a range that's representing noise, or that's representing something that you want to be different. A good example could be we could have deuterium, and I can rename the field to deuterium. And if I do that, I can run the decompose by range again, and you will then see that it creates a variable that is called deuterium, which is now representing that range which is called deuterium. Of course, you could have multiple ranges called deuterium, so you can see deuterium.pos, we've got it here now, and you could have multiple ranges that are called deuterium, and it will then all combine them to this. The same thing works, by the way, by range, but there it's pretty trivial, right? You could just rename one range, and that one range has then this different name. But there, if you go by range, then it's split up anyway. This is all well and good, but especially if you want to do analysis material, so looking at individual ions is always good if you're an atom pro person, because you can look at field evaporation effects and so on and so forth. But once you're fairly reasonably sure that you've got everything right about identifying your ions, then obviously very often you want to go to on a per atom basis. And let me clear all the variables again and just load everything in again so it doesn't get too cluttered in the workspace. Oh man, one day Matlab will actually give us the ability to make case insensitive file extension. Okay, so we've read that in again, and now we're going to do something interesting. So we can go into the range file, and we can, I know this is not deuterium 2.0, but just for argument's sake, we can say, okay, this is deuterium 2.0, and I'm not going to call it deuterium in this case, just D for short, right? So we will remain, and we'll also create a D here. Obviously, this is not actually real, okay? There is no D2.0 and no D in this data set, but just for argument's sake, okay? And then you can go in and decompose by range type, and we'll go type. So what type then will do is actually go into your the range variables and look at which unique individual string combinations separated by a space it will find, okay, or spaces. You could do two spaces as well, but just don't, okay. It will find those. And we'll say, okay, this is a variable with, or this is a range with deuteriums and one oxygen atom. And it will take care of that and give us a d.pos, which actually contains two copies of this range, shifted by a certain margin, so that we don't have atoms sitting on top of each other, which for numeric reasons can be bad, and takes the deuterium out of this range, okay? So you can create any fantasy name you want, okay? The only thing you cannot do, obviously, is use trailing numbers. You can use leading numbers, so you could use, instead of deuterium, you could use 2H, okay? You could use 2H2O, and this would work. Please don't do trailing numbers because they're obviously the multipliers. Okay, so if we now go decompose by post by range. Yeah, and there also need to be variable names that you can use as variable names, and apparently, should have tried it before, apparently Matlab doesn't like it if they start on a number, so we'll let them I2H for isotope, I don't know. And now we should get a proper decomposition of the individual ions, and yeah, so now we've got an I2H.POS, which should have exact same number of entries as our D.POS, right? Because it's the same thing. Yeah, and this allows you to work with ranges that are just noise, or work with ranges that are might be isotopic tracers, and you want to give them special names. I don't know, Johnny, Carly, whatever. And yeah, you can do that with the range names. There it's obviously a lot more trivial. Just call the range whatever you want. But you can also do it with mixed ions if you do the whole thing with with an atomic decomposition, or in this case called type decomposition. Alright, that's it for now. I'm actually currently also working on some nice mass spectrum tools to do some mass spectrum analysis straight in Matlab. So if you don't have your want to have your ranges loaded from IVAS, you want to just work in Matlab. In my case, that's obviously because I'm currently building a new atom probe, which is not going to have the IVAS data format, so obviously I have to do everything myself. So I'm currently building a nice range type editor, or a widget version of a range type editor for Matlab, and I think that's going to be posted fairly soon as well. Alright, so I hope that helps all of you out there doing your atom probe analysis, and yeah, I'm always looking forward to seeing what funky new things people do with the atom probe data when they go to conferences.